Hello everyone, my name is Tirthak Patel. I'm a PhD candidate at Northeastern University. This work was conducted as part of my internship at Berkeley lab. Welcome to our talk about Quest, a method of generating robust quantum circuit approximations using circuit synthesis. Quantum computing has potential applications in many fields, including chemistry and physics simulations, material science studies, cryptography, and general optimization problems across different sectors, including pharmaceuticals and finance. But in their current state, these computers suffer from multiple noise effects. These effects include errors related to the qubits losing their coherence, applying quantum gate operations, and measuring the qubit state, and these errors affect the fidelity of the output produced at the end of a quantum program. When a quantum program is run on a quantum computer, the hardware noise effects cause it to have errors in the output of the program. The two figures here show the output of the two quantum material simulation algorithms TFIM and Heisenberg. They output the time evolution of the magnetization of a four-spin physical system with nearest naval Hamiltonian interaction components. These are key applications that help study the complex interactions of quantum mechanical particles. The ground truth here is determined by running ideal quantum simulations classically for these smaller size problems. As the figures show, when the algorithms are run on actual quantum computers, the output is very different from the ground truth, and this is because of the high noise levels on quantum computers. So the goal of Quest is to mitigate the adverse impact of these hardware noise effects on the output fidelity of the quantum programs, and to do so by developing effective and efficient compiler optimizations. Before introducing the design of Quest, let me discuss some relevant information about the gate model of quantum computing. Different quantum computers have different number of qubits with different error characteristics and different topological structures, as shown for these small-scale IBM quantum computers. The circles here represent the qubits and the arrows represent their connections. So for example, the Melbourne computer has 15 qubits, each with 2 to 3 connections. Now each of these qubits represented by a circle can exist in a superposition of the two basis states 0 and 1. The alpha and beta are complex coefficients that represent the relative contribution of these basis states to the overall qubit superposition. When the qubit state is measured, a superposition collapses, and it can be found in one of the two basis states with probabilities corresponding to the magnitudes of alpha and beta. So the output of a qubit is a probability distribution over the two basis states. This notation for one qubit can be extended to an n-qubit quantum system. An n-qubit entangled system exists in a superposition of 2 to the n basis states, with complex coefficients corresponding to each of those states. When this system is measured, it can be found in one of those 2 to the n states, and its output is represented as a probability distribution over all of those states. A quantum program, which is also called a quantum circuit, consists of a sequence of gate operations applied to a system of qubits in order to achieve a desired qubit state. So as the example 4-qubit quantum circuit figure here shows, each qubit is represented using horizontal lines, with gate operations being applied from left to right. So here the gray squares represent 1-qubit rotation operations, and the red circles represent 2-qubit CX or CNOT gates. After applying all of these gate operations, the measurement operations are applied to determine the qubit states. Now the gates are mathematically represented using unitary matrices. A unitary matrix U is a square matrix such that its inverse is its complex conjugate transpose, which is also called as Hermitian adjoint. So here the U inverse is represented using U dagger. So the example here shows how it is mathematically represented when the gate U is applied to a state psi1 and the final state is psi2. The unitary matrix corresponding to the entire quantum circuit can be obtained by taking a product of all of the gate unitaries within the circuit. Next, we'll look at the error rates of these quantum gates and how they affect the entire quantum circuit. These quantum gates and qubits can experience errors due to the hardware noise effects, and previous state-of-the-art works have attempted to mitigate those errors using mapping and post-correction techniques. These techniques include taking an average of multiple best mappings in the ensemble of diverse mappings work, using operation error-aware mapping in the Eureka work, performing error variability-aware mapping and statistical correction in the Veritas work, and then using the reversibility property of quantum computing to post-correct the output in the Craft work. But all of these works have not looked at the concept of alternative ways of generating circuits by reducing gates with very high error. Now these noise effects can be especially pronounced for 2-qubit CX or CNOT gates that are used for entanglement. A typical quantum circuit requires many 2-qubit CNOT gates across the different qubits. These gates have an order of magnitude higher error rate than 1-qubit gates, so their error footprint on the program is significantly larger. And this is especially true as quantum circuits become larger and have more CNOT gates. So if we can reduce the number of CNOT gates in a quantum program without changing the functionality of the program, it could greatly help for reducing this error. So we propose the concept of coarse-grained circuit approximations. What if we can generate approximations of quantum circuits with much fewer CNOT gates than the original circuit? Fewer CNOTs can help us reduce the circuit size and improve the output fidelity. I should note here that the approximations of quantum programs are not similar to approximations of classical programs. In classical computing, approximations are used to improve the performance at the cost of program fidelity. On the other hand, in quantum computing, approximations can help us improve the output fidelity. Now there are infinite ways of achieving the same quantum functionality, but we want to specifically select ways that result in low CNOT counts. We achieve this by using the procedure of approximate synthesis. In synthesis, we have a target of ensuring that the distance between the unitary matrix represented by the original circuit and the unitary matrix represented by the approximate circuit is under a certain threshold. In the formula shown here, U dagger is the conjugate transpose of the original circuit matrix, U prime is the approximate circuit matrix, and n is their dimension. If we take a trace of their product and normalize it, we get the Hilbert-Schmidt distance, and this distance needs to be less than an arbitrary threshold epsilon. So how exactly is the approximate circuit generated using synthesis? Well, it is constructed layer by layer. First, we have the initial qubits with parametrized 1-qubit gates. To this state, we add a layer of CNOT and parametrized 1-qubit gates. We optimize the parameters of the gates such that the Hilbert-Schmidt distance is minimized. If the distance is greater than epsilon, then we add another layer of gates and again optimize the parameters. And this is done until the distance becomes less than epsilon. If epsilon is too small, then the approximations will be fine, and that will require deep circuits with a lot of CNOT gates. So we need epsilon to be large enough so that the generated circuits have fewer CNOT gates, but the approximation output still matches the output of the original circuit, and this is tricky to achieve, as we'll see next. The primary challenge that we face here is that because of the requirement to calculate circuit distances between circuit unitaries, it is computationally infeasible to calculate circuit distances for large circuits. This is because the dimensions of the unitary scale exponentially with the number of qubits in the circuit. So to mitigate this challenge, we need to partition the circuit into manageable independent blocks. So for example, say we have a 4-qubit circuit that we cannot deal with computationally. We can partition it into two 3-qubit blocks as shown here. The partitions have to be independent from each other. That is, there cannot be a CNOT gate between the two partitions. In this example, we partitioned the circuit represented by U into circuits represented by U1 and U2. The partitioning procedure to generate the minimum number of blocks is an NP-hard problem, so we have to use the more computationally efficient yet effective approach of scanning the circuit from the front of the circuit to the back of the circuit and forming the blocks along the way. A frontier is maintained for all of the qubits, and at each step of the block formation procedure, the largest possible block is formed among all possible ones. Then the frontier is moved forward for the qubits of that block, and the process is repeated until all of the operations in the circuit are covered. We can then perform the synthesis procedure individually on these blocks. So for U1, we can generate an approximate circuit such that the distance is less than the epsilon 1, and do the same for U2. Once the approximations are generated for both the blocks, the circuits can be patched back together. However, there is a problem with this approach. Because individual blocks have their own approximation thresholds, when these blocks are put back together, the overall approximation error of the circuit may become very high. This is because we do not know how the approximation errors of individual blocks combine and interact with each other. So to overcome this issue, we needed to prove a bound on the overall approximation error of the circuit, given the approximation errors of the individual blocks. Now let's see how this bound works. We will prove the bound for the example 2-block circuit we've seen, and then the proof can be extended to larger circuits for n blocks using induction. The first step in this proof is to extend the error of blocks that are on a subset of the qubits to all of the qubits in the circuit. This is because other qubits are idle or can be seen as running the identity operator, while the other block is running on a subset of the qubits. In this example, U1 needs to be extended to 4 qubits even though it is a 3-qubit block. So if we follow the steps here, we can show that the Hilbert-Schmidt distance of U1 when extended to all 4 qubits is still epsilon 1. The same can be shown for U2 as well. We now expand U to the extended versions of U1 and U2 and apply trace commutativity and inequality laws and find that the Hilbert-Schmidt distance of the overall circuit is bounded by the sum of the approximation errors of the 2 blocks. If we generalize this to an n-qubit circuit with k blocks, we find that the Hilbert-Schmidt distance of the full circuit is additively bounded by the sum of the bounds of individual blocks. This is a powerful result because it means that we simply have to ensure that the sum of the block approximation errors of individual blocks is less than our desired threshold. But this leaves us with ample room to down-select blocks as synthesis generates hundreds of approximations for each block, so we need to carefully select among these approximations. We achieve this by meeting 2 criteria. The first is that our overall goal is to ensure that the number of CNOTs in the selected approximations is minimized. The second is that we want to select approximations such that their output is close to the output of the original circuit. Because we want the number of CNOTs to be minimized, our approximations have to be coarse, and we need to select multiple approximations in a manner that their average mimics the output of the original circuit. So this is shown visually by the example here. We have the original circuit output, which is shown as a red cross, and around this cross is the boundary of the Hilbert-Schmidt process distance. All selected approximations need to have an overall error within this boundary, as we saw in the bound earlier. This boundary is kept large so the approximations can be coarse and the CNOT count can be minimized. Now if we select just one approximation as shown in the first circle, its output can be far from the output of the original circuit. But if we select multiple samples such that they cover different regions within this boundary, then the average of their output can imitate the output of the original circuit. And this is shown by the last circuit where we have 5 samples, and these samples are divided within the boundary, and their average is close to the red cross. So overall, the approximations are selected one by one with half weight placed on minimizing the CNOT count, and other half of the weight placed on ensuring that the new selected samples are different than the previous ones. So to summarize, this is the overall 3-step procedure of Quest. First, the circuit is partitioned into blocks of manageable size using a scalable partitioning technique. Then, approximate circuit synthesis is performed for each of the blocks in parallel, and multiple approximations are generated for all of them. And lastly, among these approximations, the ones that have low CNOT counts have diverse mathematical characteristics and are within the theoretical approximation error bound are selected. These approximations are then run on quantum computers, and their output is averaged to generate the final output estimation. Now let's look at some evaluation results. Quest is evaluated for a variety of algorithms of different sizes and use cases. The plot here shows the reduction in the CNOT gate count compared to the original synthesized circuit. The y-axis shows the percentage reduction in CNOT gate count with Quest and other compiler optimizations available with IBM's Qiskit compiler. We observe that Quest reduces the number of CNOTs by 30% on average, and over 50% for some algorithms like TFIM, XY, and Heisenberg. Next, we look at the faithfulness of the average output of Quest approximations to the output of the original circuit in the ideal scenario. These figures here show the total variation distance and the Jensen-Shannon divergence among the approximated and original outputs. As both of the metrics are low across different algorithms, it shows that Quest is able to be faithful to the original circuit output. The reduction in CNOT gate count directly impacts the output fidelity of the quantum programs. The figures here are similar to the figures that we saw at the beginning of the talk, with additional lines representing Quest. Recall the existing compiler techniques of Qiskit were not able to accurately get output close to the ground truth, but with careful selection of approximations with Quest and the reduction in the CNOT gate counts, we see that Quest is able to track the ground truth output much better across the different evolution time steps. Our paper covers many more experiments related to the performance of Quest in achieving high fidelity output. These include results related to running more algorithms on current quantum computers, detailed case study of how Quest performs for specific algorithms, the computational time of Quest, sensitivity to techniques like the approximation threshold, and results related to simulating different noise levels keeping in mind the future improvements in hardware noise. Please refer to the paper for these additional results. With that, I conclude this presentation on Quest. Please access the DOI link or contact me for further information.